Picture this: the vast, mysterious universe, with all its stars, galaxies, and quantum quirks, might actually be describable using just one fundamental building block: time itself. It's a mind-bending idea that could shake up how we understand reality, and if you're curious about the cosmos, this is the revelation you won't want to miss. But here's where it gets controversial. Physicists have long debated just how many constants we truly need to unlock nature's secrets. Stick around, because this latest research might just prove that time is the ultimate key. Back in 1992, during a casual chat in a CERN cafeteria, three brilliant minds, physicists Michael J. Duff, Lev B. Okun, and Gabriele Veneziano, found themselves at odds over a deceptively simple question: how many constants does it really take to define the entire universe? Their lively disagreement sparked a chain of ideas that culminated in a recent groundbreaking paper, suggesting we might need only one: time. As a published author specializing in the weird and wonderful realms of science and history, I've always been fascinated by these kinds of cosmic puzzles, and this one feels like a game changer. For those just dipping their toes into physics, let's break it down gently. If you've ever pondered the workings of the universe, and who hasn't, you've probably encountered fundamental constants, those unchangeable numbers that underpin everything from gravity to light speeds. These aren't things we can deduce from theory alone, we have to measure them experimentally in the real world. Think of classics like the speed of light, often denoted as c, Planck's constant, which dives into quantum mechanics, or the fine structure constant, that peculiar number around 1/137, which baffles even seasoned experts because it seems so arbitrary. As Martin Rees, the esteemed emeritus professor of cosmology and astrophysics at the University of Cambridge, puts it in an article for The Conversation, these constants represent the fixed parameters of nature, like the gravitational constant, g, or the speed of light. We plug their values into equations to predict how the world behaves, yet our theories can't explain why they have the values they do. It's as if the universe chose these numbers at random. Why not different ones? Physicists have tirelessly measured these constants with incredible precision, and they've shaped our modern system of units. The International System of Units, SI, relies on 7 base units: seconds for time, meters for length, kilograms for mass, amperes for electric current, kelvins for temperature, moles for amount of substance, and candela for luminous intensity. But the big question remains: how many of these do we actually need? The new paper, led by George Matzes from the Institute of Theoretical Physics at the São Paulo State University, builds on that 1992 debate and argues for just one: time. The story begins with the three physicists publishing papers in 2002, each proposing a different number. Okun suggested 3, length, mass, time; Veneziano went for 2, length and time, and Duff believed it depended on the model. The goal is to find the most fundamental description of physics possible, Matzes explains in a statement. The question raised by Okun, Duff, and Veneziano is by no means trivial. As physicists, we're faced with the need to understand what's the minimum number of standards we need to measure everything. And this is the part most people miss. Their latest work explores 2 types of spacetime to test the idea. First, there's Galilean spacetime, the straightforward model Isaac Newton used before relativity complicated things. In this view, space and time are totally separate, time flows uniformly for everyone, and distances don't bend or warp with motion. You need both a ruler, for length, and a clock, for time, to measure everything, and even mass can be defined from these basics. But switch to Minkowski spacetime, the relativistic framework from Einstein's theories, and things get truly fascinating. Here, space and time aren't independent, they're interwoven, meaning you can derive one from the other. In Galilean spacetime, you need rulers and clocks to measure all the physical variables. In relativistic spacetime, however, clocks are sufficient, Matzes notes. High-precision atomic clocks, like those ticking in labs today, could handle all measurements because relativity shows how movement affects time. To illustrate with an example, imagine trying to measure the length of a rod without a ruler. Tricky, right? The team draws on a clever 3-clock experiment by physicist Bill Unruh. Picture 2 observers, one at each end of the rod, with clocks synced up. One sends a clock along the rod to the other, who adjusts his own based on the arrival. Send it back, and voila, using the time differences, affected by relative speeds in spacetime, you calculate the length accurately. No need for extra constants like the speed of light, time does it all. In essence, the researchers propose that every physical quantity, mass, length, energy, can boil down to seconds. Our current definition of a second is precise, the duration of 9,192,631,770 periods of the radiation corresponding to the transition between the two hyperfine levels of the ground state of the cesium-133 atom. It's a testament to human ingenuity, but this simplification raises eyebrows. And here's where it gets controversial. While this paper suggests we could ditch other constants, don't expect them to vanish from textbooks or labs anytime soon. They're incredibly practical. As Daniel Vanzella from the São Carlos Institute of Physics at the University of São Paulo adds, historically, based on a standardization effort adopted during the French Revolution, 1789 to 1799, the kilogram was defined as the mass of 1 liter of pure water at a given pressure and temperature. In practical terms, it's very convenient to have a mass standard, but from a fundamental point of view, it's not necessary. He explains that mass emerges from acceleration at a distance. Think of how gravity pulls on objects. This study, published in Nature Scientific Reports, challenges us to rethink the foundations of physics. Is time truly the master constant, simplifying everything to a single thread? Or does this overlook the beauty and complexity of multiple parameters? Some might argue it's a radical step toward unifying theories, while others see it as ignoring the richness of diverse measurements. What do you think? Does reducing the universe to time alone make science more elegant, or does it strip away essential layers? Could this lead to a multiverse where constants vary wildly, or is it just a clever thought experiment? Share your opinions in the comments. I'd love to hear if this sparks debate or inspiration for you.